Okay, let's do a quick overview of numerical integration. So sometimes analytical methods won't work. When we say analytical methods, we mean things like integration by parts, partial fractions, trig sub, or use of, or any other of the straightforward procedural steps to get a single function as an answer for an antiderivative. Sometimes that doesn't work. There are some things that simply just don't have an antiderivative. A really quick example of one that does not have an analytical antiderivative would be sine of x squared. So there's no way for me to evaluate this one exactly. So we have to estimate it. And that's what numerical integration is going to be all about. So suppose that if you have some numerical estimation that we're going to do, we'll call that C. That could be our estimation, and then X, let's say, is the exact solution if there is such a thing that I could find. Then the absolute error would be the absolute value of the difference between the two, and then the relative error is the absolute error divided by the magnitude of the exact answer. So that's one of the definitions. And then there's three main things for 3.6. The first one is midpoint rule. This should be a quick review of Calc 1. That's just Riemann sums. All we're doing here is Riemann sums. So we are going to pick a number of rectangles that you want to do, find the area of each of those rectangles, and then add them up, and that's going to be the estimate. So most of that should look pretty familiar. I'm going to leave that theorem up in case you want to be looking at that while we work through it. But let's look at this example. Approximate the integral from 1 to 9 of x cubed using the midpoint rule with n equals 2 and 4 subintervals. Let's go ahead and just skip the n equals 2. Let's just jump straight to the 4 subintervals. That will just become a little bit easier just to get used to this stuff along the way. So step 1 is to find your delta x. So that's still going to be the first thing that we're going to do. So delta x is b minus a over n. So in this case, that's 9 minus 1 over 4 subintervals, which is 8 over 4, which of course is just 2. So the next thing I'm going to do is draw a picture so you can see what the midpoint rule really is. So here is my graph of f of x equals, in this case, it's x cubed. Of course, every one is going to be slightly different. We're starting off with a nice easy one, and I'm trying to evaluate that from 1 to 9. Is what we're looking at here. That's from 1 to 9, and we're going to break it up into 4 subintervals. So that's what we're going to do. And then each one of those subintervals has a width of 2. That was what my delta x is. So that means it went from 1 to 3 to 5 to 7 to 9. It had a width of 2. And then what we're going to do for the midpoint rule is find the point smack dab in the middle, and then use the midpoint to draw the height of each of those rectangles. All right, that's what we're going to do. We're going to find that midpoint and then use the midpoint to draw the height of each one of those rectangles. And then we'll just find the area of each of those rectangles and add them up. So once you have your delta x, the picture, you may or may not need to draw the picture every time. I certainly recommend it. It's more visual, but you certainly don't have to. The next thing, I'm going to just list out, I'm going to actually just skip straight to the midpoint. We're going to list out all of the midpoints, and then I'm going to find their y values right after it. To me, that tends to be a little bit easier. So my midpoints of each of those subintervals right in between 1 and 3 was just 2. And then the next one right in between 3 and 5 was, of course, 4. And then 6 and then 8. Those are each of them, the midpoints on the x-axis. Those are the midpoints on the x-axis. And then I like to find the y values right now just so I don't lose those. So each of those midpoints, find the y values because that'll be the height of each of those rectangles. So 2 cubed is 8, and then 4 cubed is 64, and then 6 cubed, I'm plugging that into the function, would be 216, and then 8 cubed, yep, it's 512. Okay, and then we're going to go ahead and estimate it. So I'm going to write this down here at the bottom with the correct notation. The integral from 1 to 9 of x cubed dx is approximately equal to the midpoint rule with 4 subintervals. And that's just going to be, you're going to add up, first of all, the height at 2 times the width, and then plus the height at 4 times the width plus the height at 6 times the width plus the height at 8 times the width. And the width of each of those rectangles was delta x. So 8 plus 64 plus 216 plus 512, all times that common width of 2. And that's what we're going to end up with. And I'll type that into my calculator right now and see what we got. 8 plus 64 plus 216 plus 512. And then all times 2, I got 1600. Ta-da. Okay, that's really just Riemann sums. So maybe you did left Riemann sums and right Riemann sums in Calc 1, and here is the midpoint rule for Riemann sums. So now what we have to do is do a better estimate. As you might have guessed, really the midpoint rule maybe isn't the best estimate in the world, so we're going to come up with better estimates to calculate the area under the curve. So the next one would be what's called the trapezoid rule. And so here's a formula. You can write down the formula and memorize it. That's one way to do it. But I think a better way to do it is to actually understand where it comes from. And this one's actually a pretty easy one to understand where it comes from. So I highly recommend that you draw this picture out. If you know where it comes from, you'll be able to apply this to all types of things later on. So I'm going to draw some arbitrary function. Here is my function f of x. And we're going to, let's say, have a starting and an ending x value that I'm looking to find the integral underneath. Or sorry, let's call it the area, but it is just the integral in this case because everything is positive underneath that function from a to b. And let's say I just break it up into a couple of different pieces. I don't know, I'll do 4, but you can imagine I could do 5, 6, 7, 8, 9, as many sub intervals as I'd like. What I'm going to do now is find, instead of rectangles, find trapezoids. That's really all that we're going to do. So instead of drawing this rectangle straight across, I'm going to actually just draw that slanted line for each one of these. And you can see maybe some of them are above, maybe some of them are below. They're all just going to be good estimates. And we're going to have the area of each one of those trapezoids. So let's label those points. We'll call the first grid point x0, then x1, x2, x3, and x4, just to list out those grid points. And we're going to try to calculate the area of each one of them. I'll just start off with the first couple. We're going to have to just find all of them. So maybe you remember the formula for the area of a trapezoid. Maybe you don't, but I think it's worthwhile to know where it comes from. Because otherwise we're just memorizing formulas without any meaning. So let me give you a good idea of where the formula for the area of a trapezoid came from. So here is just a trapezoid that I've drawn. I'm going to label some things on that trapezoid. I'm going to call the width of that trapezoid delta x, or maybe really we can just be simpler. We can just call it b for base. It doesn't really matter what you call it. And then notice that this trapezoid has 2 different heights. So I'll call that height 1 and height 2. It doesn't matter which one you've labeled which. Now I'm looking for the area of this. You could break it up into a rectangle and a triangle and then find the area of each of them and add them together. That's not too bad. It's not, it would totally work. It's a little bit more algebraically annoying. So I'm not going to do it that way, although I promise you it's totally possible. So what I'm going to do instead, though, I'm going to take that trapezoid that I have, and I'm going to just duplicate it. I'm going to draw it again off to the side over here, and then I'm going to flip it upside down and put it right on top of itself. And if I do that, then you should notice that this would have then become my height 1 and my height 2 over here flipped sides. And now I have a full perfect rectangle. And I know how to find the area of a rectangle. The area of a rectangle is just base times height, right? And so what I'm looking for is the area of half of it. So my area of my trapezoid will be half of the area of this entire rectangle that I'm looking at, which would be 1/2 times the base times the height of this rectangle. And hopefully you can see now the height of this rectangle, no matter which side you're measuring, the left and the right, it's a perfect rectangle, so it doesn't matter. It's just going to be height 1 plus height 2. So in fact, it's height 1 plus height 2. That's the area of one of those trapezoids. Cool. Okay, so now we have the area of a trapezoid. That's pretty good. I'm going to kind of pull that off to the side and leave that off to the side. Let's go back to our calculus though. Let's go back to our calculus. Let's find the area of these particular trapezoids because I've got 4 of them in this case that I want to add up. We're going to find the area of that trapezoid. I'm trying to find the area technically of the whole area under the curve, and we're estimating it with trapezoids. So maybe a better notation would be reminding us that we're actually looking for the integral from a to b of this function, and we're estimating it by adding up the areas of those trapezoids. Right, that's one the notation that you can use. If you want, though, can use the trapezoid notation, which would just be t sub 4 in this case. That's really all that would, because I just did 4 rectangles. Maybe you wanted to do 5, I don't know. All right, so each one separately. The first trapezoid would be 1/2 times the base times the height 1 plus height 2. Now the base, we already called the base delta x, just like we did before in left Riemann sums, right Riemann sums, and midpoint Riemann sums. We did all those as the same. So that's just delta x, that's my base. And then I need the height 1 plus height 2. Well, it looks like height 1 plus height 2 are the 2 different y values at x sub 0 and x sub 1. So this would be f of x sub 0 plus f of x sub 1. Okay, and then I have to go plus, then I have the second trapezoid. So 1/2 times the base times the height 1 plus height 2 of this second trapezoid. And you can see from there that that height 1 would be the y value at x1, and then height 2 would be the y value at x2. So I would label that as f of x1 plus f of x2. Okay, and then plus, and then I'm going to do the same thing. Now I'm on to this third trapezoid. I might as well finish it off. It's still going to have a 1/2 base times the height 1 plus the height 2. It looks like there goes f of x2 and f of x3. So f of x sub 2 plus f of x sub 3 plus, and now I'm on to the fourth trapezoid, and it's the same idea. So 1/2 delta x, f of x3 plus f of x4. Okay, and then I'm going to notice another thing that we can do. Notice all of them have a 1/2 and a delta x in common. No problem. They all have a 1/2 and a delta x in common. So I can factor that out. And I really could, and if you did it that way, that would work. It would be correct, I promise. What if I chose instead to just factor out the delta x? Or I promise no real reason. They're just fractions are going to be either on the inside or on the outside. It doesn't matter. It really doesn't. If I were to start distributing this across the 1/2, excuse me, if I were to distribute the 1/2 across, I would end up with the first one would be 1/2 f of x sub 0 from distributing that 1/2 here. The second one would be 1/2 f x1 plus, and then I would have this third one over here. Once I distributed that, would be 1/2 f of x1 plus 1/2 f of x2 plus, and I could keep going. I would have to distribute this one and this one. I just want you to notice what happened. You see how these ones are like terms? So half of f of x1 plus half of f x1 would be just 1 of f of x1. So those would combine, and then you can imagine the next two would combine as well. You should notice that the x2s will combine and the x3s will combine. The only ones that did not was the x0 and the x4. So then we have now delta x times 1/2 f of x0 plus 1 f of x1 and 1 f of x2 and 1 f of x3, and then 1/2 of the last one that didn't have anything to combine with. And that's where we get the formula from, okay? So the first and the last got the extra 1/2, the ones in the middle did not. Okay, so that's where the formula is going to come from. Now you know where it's coming from on that previous page that I was showing you guys. Now we can use the formula. So that's the trapezoid rule. It's just maybe another way to do a numerical integration. So let's practice it. Approximate the following integral using the trapezoid rule with n equals 6 subintervals. So first thing that you should do is find your delta x. That should always be the first thing that we do. So my delta x is b minus a over n, which in this case would be 1 minus 0 divided by 6. The next thing I'm going to do is I'm going to find my grid points. I'm going to find all of my grid points. I don't need to find the midpoint here, because we did the trapezoid rule here, not the midpoint rule, but I do want to find all of my grid points. And if you start counting at x sub 0, you're going to start at the very beginning of your interval in question. So if this was the integral from 1 to 5, then your x sub 0 would be 1. If it were an integral from 1 to 3, then your x sub 0 would be 1. If it were an integral from 5 to 7, then your x sub 0 would be 5. It's always whatever the starting value is, which in this case just so happens to be 0. And then all I have to do is add delta x. So 0 plus 1/6, because my delta x was 1/6. And then I'm going to add another delta x, which is 2/6, which I can, of course, reduce. And then I'm going to add another delta x. And then I'm going to add another delta x. And then I'm going to add another delta x. And then I'm going to add another delta x. You keep going until you get to the ending value of your interval in question, which in this case was 1. So now I'm good here. I can stop there and I have all of my grid points. And then I can do my trapezoid rule. So the integral from 0 to 1 of e to the power of x squared dx is approximately equal to the trapezoid rule with 6 subintervals, which was, and let's go back and remind ourselves what it was. I had to have that delta x, whether you put that at the beginning or the end, doesn't matter. And then we were adding up all of the heights of these trapezoid rules. Remember, in the first and last one got the 1/2, but the ones in the middle did not. Because we saw how those were like terms and they combined. We saw that on the previous page. So I'm going to have my 1/2 f of 0 plus f of 1/6 plus f of 1/3 plus f of 1/2 plus f of 2/3 plus f of 5/6 plus 1/2 f of 1, all times my delta x. And then I can plug each one of those in, and that's going to become 1/2 e to the 0 squared, and e to the 0 is 1, plus e to the 1/6 squared, plus e to the 1/3 squared, plus e to the 1/2 squared, plus e to the 2/3 squared, plus e to the 5/6 squared, plus 1/2 e to the 1 squared, all times 1/6. And of course, feel free to type that into your calculator if you'd like a decimal. Okay, so that's the trapezoid rule, which works out kind of nice. It's a little bit smoother compared to the midpoint rule or the left Riemann sum or the right Riemann sum, but it's just simply another way to get a numerical approximation. Okay, that's what we were looking for here, with a numerical approximation. That was another way. Okay, so the next thing I'm going to do is talk about an error. We won't be able to prove these formulas in this class, but these formulas will be given to you on any exam if you need them. But we're going to talk about how to use these formulas. The proof is in your textbook. It's kind of talked about a little bit more in the appendix. It's a bit above and beyond the requirements, I think, for this class. So that's why we're not going to talk about it here. But this is going to help us find how off I am. How good of an estimate is it really? So it's an error bound for both the midpoint rule and trapezoid rule. So basically what it is it can tell me what the error actually is going to be. Now, not an equal sign. Notice I don't know the exact error because I'm still just estimating here. I don't know the exact value, but I do know what the error is going to be smaller than. So the error is going to be smaller than this guy for both the trapezoid rule and the midpoint rule. We're going to focus on the trapezoid rule for right now. So I'm going to leave up that formula for the trapezoid rule, but in fact, I should maybe leave the whole formula up. We don't need it all. So find the minimum number n of subintervals needed to approximate the value of the integral from 0 to 1 of e to the x squared with an error less than 0.0001 using the trapezoid rule. So I have a formula for the trapezoid rule, which is right here. So A and B I know, N is what I don't know, it's what I'm looking for, it's asking me to solve for N. I need to figure out what my M is, capital M. So let's go back and read this. M is the maximum value of the absolute value of f double prime of x over the interval from a to b. So it's the maximum of f double prime, which has to do with concavity. So maybe that helps you visualize why that f double prime might be in here. It does have a lot to do with the concavity, to help you figure out how off your trapezoid rule is. Are you above or below? Things like that. Okay, so I just need the f double prime. That's really what it is that we're looking for here. So my f of x is e to the x squared. So f prime of x is the derivative of e to the something is just e to the something, but times the derivative of that something that was chain rule. And now I'm going to do f double prime of x, which now you should see you're going to do a product rule. So the derivative of the first one, leave the second one alone, plus leave the first one alone, and the derivative of the second. I'm still doing product rule and chain rule involved here, and I'm going to simplify. That's e to the x squared times 4x squared plus 2. I have the second derivative, and I only care about that second derivative on the interval from 0 to 1 because that's the bounds on my integral. And I want to try to find the maximum value. So maybe you think of your Calc 1 stuff and you would take the derivative of this guy, find its critical point, plug the critical points in, plug the end points in to get your max and your min. I only need the maximum value though. So rather than doing all of the Calc 1 stuff, I'm just going to show you the graph. I think it's worthwhile to just see the graph so you have a general idea of how to go about doing that. So I've just graphed the second derivative here on Desmos. I specifically graphed it to be only between 0 and 1. And you can zoom in if you'd like to try to take a look at that. That is the graph, not of the function that I'm trying to find the area of, but of the actual second derivative. And I just noticed that it kept increasing the whole time. So clearly the maximum value would be the value at 1. So I plugged in 1 and I got the value of 16.31. So that means that my m, I should write that down, sorry, is equal to 16.31. Cool. All right, so now I have my m and I have the formula for the trapezoid rule error. So I'm going to write that down. So it's going to be the error in the trapezoid rule. I'm just going to use e for error, is less than or equal to m times b minus a cubed over 12n squared. Plug in what I have. So what I have is 16.31 times 1 minus 0 cubed all over 12n squared. N is the unknown, so it's what I haven't found yet. And in this case, the question says I want this to be less than 0.0001. And then you just solve for n. This is now, honestly, this is all I have to do now is just solve for n. So I'll just go through and do that nice and slow. So 12 over n squared, sorry, 12 times n squared over 16.31 is bigger than 1 over 0.0001. When you flip both fractions, I just flipped both fractions, and then I can flip the inequality because I'm just trying to get n by itself. So I got n to not be on the bottom, and then I'm going to go multiply. I'll use my calculator here. So let's do that. 1 divided by 0.0001, and then times it by 16.31, and then divide it by 12. And I got n, let me write down what I have. N is bigger than 1. It's actually n squared. Sorry, I haven't taken the square root yet. 6,667. So maybe I should do that. I'll take the square root of that answer. And I got n is bigger than 116.58, which means that n, you can't have half of a trapezoid. We're doing trapezoid rule where everything is equally spaced. Should be bigger than or equal to 117. So just to get the first 3 decimal places correct, I need 117 trapezoids. This hopefully helps you realize how important numerical integration is, because it's definitely just an estimate. So we need lots and lots and lots of terms to get us a good value. So that's probably going to be where the computers are going to come into play. And it's good to notice that you might also just want to do analytical if you actually can solve it analytically, because 117 is kind of a lot. But there it is. Now I have it. So now I know how many terms I would need, write up a computer program to calculate those 117 trapezoids for me, and then I would get the estimated area underneath that curve. Ta-da. Cool. All right. So there is one other possible method for numerical integration, and that's Simpson's rule. Simpson's rule, what it does is it takes your area, I'll do a quick little graph here, and it takes each little sub-interval and it turns it into instead of a trapezoid or a rectangle, it turns it into a parabola. So it turns it into a parabola instead, and then finds the area under that parabola, so it's a slightly better estimate, which means you might need less sub-intervals to get a better estimate, which is why it's kind of nice. But there it is. This is not a formula that we're going to prove. It's just the area under a parabola, not particularly exciting. But I promise you this is a formula that would be given to you if it were to show up on an exam. So here's the formula for the Simpson's rule. Let's just calculate it. So we'll leave the formula up there. Step one is to find your delta x. So delta x is always b minus a over n. So 1 minus 0 over 8 in this case. So my delta x is 1/8. And then I'm going to find all of my grid points so I don't lose those. X sub 0 is 0, x sub 1. You add delta x. I'm going to add another delta x. So 2/8 would give me 1/4. And then I add another delta x. And then I add another delta x. And then I add another delta x. Yeah, there was, I think I missed the 5 over 8, sorry. 5/8, there we go. X sub 6 would be 3/4. 7/8, and then 1. So I just added up delta x along the way. All right, so now I have all my good points, and then you have your formula. So the integral from 0 to 1 of sine of x squared dx is approximately equal to the Simpson's rule is what we were using here, which is just going to be delta x over 3 times, truly just plugging it into the formula, by the way, truly, this is a plug and chug. So f of the first one plus 4 times f of the second one plus 2 times f of the next one, and then 4 times f of, sorry, the next one, which is 3 over 8. There we go. So you alternate between 4 and 2. And then the first and last one had nothing in front of them, not a 4 or a 2, just a 1. And then you can type all that in. So I'm going to write that down. That's 1 over 24 times sine of 0 plus 4 times sine of 1/8 squared plus 2 times sine of 1/4 squared plus etc., etc., etc. Once you type all of that into your calculator, just make sure that your calculator is in radians mode, and that'll be the estimate. All right, that's all there is for numerical integration. Thank you.